Hello friends, welcome to Civil Diaries, and today we will be discussing about a very important topic of applied mechanics, and that is the free body diagram. So what is a free body diagram? The force analysis of a structure is made in a simplified way by considering the equilibrium of a portion of the structure. And for that particular portion, we will be drawing that portion separately, showing altogether three things, and those things are applied forces, the self-weight, and the reactions at the point of contact. So what are the guidelines for drawing the free body diagram? There are altogether 5 guidelines for drawing the free body diagram. The first point suggests us that there should be no external supports or connections. That means whatever external supports or connections are there to the body, we'll be removing them while drawing the free body diagram. The second point suggests us that the self-weight should be indicated with the vertical arrow downwards. So we'll be representing the W component, that is the self-weight, with a vertical arrow downwards acting through the centroid of the body. The third point suggests us that the reactions from the supports and connections should be indicated. So after removing the supports and connections, we'll be indicating the reactions from those particular supports and connections while drawing the free body diagram. The fourth point suggests us that the tension in rope or a string should be indicated towards the support. So if the body is hanging with a rope or a string, then we will be representing the tension in that particular rope or a string towards the support while drawing the free body diagram. The fourth guideline over here suggests that the adopted coordinate system and the sense of unknown force should be shown in the free body diagram. So this basically means that whatever coordinate system and the direction of unknown force that is adopted, that needs to be shown while drawing the free body diagram. And later on, the adopted directions might need to be corrected depending on whether our result appears positive or negative. I know these all might appear to you a bit confusing, but let me assure you that after digging into some examples relating to free body diagram, all these guidelines will appear much more clearer than ever before. Having all that being said, let us move on to some examples relating to free body diagram. So the first example over here is of a sphere resting on a frictionless plane surface. So we can clearly see that there is a sphere that is resting on a frictionless plane surface. Here the frictionless means that there is no friction that acts between the sphere and the plane surface. Now if we are to draw the free body diagram for this figure, we will just draw the sphere as I already did here. And the very first thing that we are gonna do according to our first guideline is we are not going to draw any supports or connections. That is to say, we will not draw the plane surface. And then according to our second guideline, we can draw the weight component, and that should act in vertically downward direction. And that should act through the centroid of the sphere. As we have already removed the support from the sphere, now we can show the reaction R at the point of contact with the surface. So this should act in upward direction and normal to the surface. So this is the reaction R. The second example over here is that of a circular roller hanging by a string and resting against a smooth frictionless vertical wall. So we can clearly observe in the figure that there is a roller that is hanging by a string and it is also resting against a smooth vertical wall. So if we have again a smooth wall, that basically means that there is no friction between the roller and the wall. Now if we are to draw the free body diagram for this example, we will draw a sphere as I already did here. The very second thing that we are gonna do is we'll be representing the weight of this roller in vertically downward direction, and that should act through the centroid. As we have the contact point B, that is the point of contact between the roller and the wall, so after removing the support, that is the wall, there appears to be a wall reaction, and that should act at point of contact normal to the wall along the BC. So we can draw it like this. And name it as RB. That basically means the reaction at contact point B. We also have the string which hangs the roller from the wall. So there is obviously tension in the string. So according to our fourth guideline, the tension in rope or string will be indicated towards the support, that is towards the point A. So we'll be representing it like this, towards the point A. So this is our tension in the string. The third example over here is that of a sphere resting on a V-shaped groove. As we can see in the figure that there is a sphere that rests on a V-shaped groove, so that there are two contact points, that is contact point A and the contact point B, meaning that there should be two reactions at contact point A and B and the weight component that should act through the centroid. So let us draw the free body diagram for this example. We will draw the sphere as I already did here. Secondly, we will be representing the weight component in vertically downward direction. This is W that should act through the centroid of the sphere. Then at the contact point A, the reaction force RA appears. And this should be normal to the contact point A, and we will name it as RA. Similarly, RB should also act normal to the contact point B, so we will draw it like this. That is normal to the contact point B, and we will name this as RB. The fourth example over here is that of a uniform ladder leaning against a smooth wall and resting on rough floor. So in the figure we can see that there is a uniform ladder that is leaning against a smooth wall. That means there is no friction between the wall and the ladder. But the ladder rests on rough floor, means that there is friction between the floor and the ladder. Altogether, there are two contact points, that is the contact point A and the contact point B. That means there should be two reaction forces RA and RB. So for drawing the free body diagram for this particular example, we will be drawing the line diagram as I already did here. The very first thing that we will do is we will be representing the weight component in vertically downward direction. So this is the weight component that is acting in vertically downward direction and at midway of the ladder. Secondly, at contact point A, the reaction force RA should appear normal to the surface. So here RA should act normal to the contact point A. Now as the floor is rough, so there is friction between the floor and the ladder, meaning that at contact point A, the frictional force FA should appear. The tendency of the ladder to slip on the floor is on this side, so that the frictional force should appear opposite to this direction on this side. So in free body diagram, we'll be representing it like this. This is FA. Similarly, at contact point B, there should be the reaction force RB that should act normal to the contact point B. So we'll be drawing it like this. This is RB that acts normal to the contact point B. There is no frictional force as the wall is smooth. The fifth example over here is that of two spheres X and Y placed in a vessel. So we can clearly see that the sphere X and Y are placed in a vessel, so that A and B are the point of contacts of a sphere X with the vessel. Similarly, E is the point of contact of a sphere Y with the vessel. Likewise, point D is the point of contact of a sphere X and Y. We'll be analyzing the free body diagram of X and Y separately and then combine it to understand it better. So let us draw the free body diagram for a sphere X. We will draw the sphere for the sphere X like I already did here. Now we'll be representing the weight component of a sphere X in vertically downward direction, and that should act through the centroid C1. So this is the centroid C1, and the weight component should act in vertically downward direction, that is the W1. As we have two contact points A and B, So we should draw two reaction forces normal to the contact points A and B. So let us do that. This is the reaction force at contact point A, that is the RA, normal to the contact point A. And this is the reaction force at contact point B, that is RB, normal to the point B. And now for the contact point D, the reaction force needs to be shown like this. We will name it as RD, that is normal to the contact point D, and it is towards the sphere X. Now let us draw the free body diagram for a sphere Y. We will show the weight component in vertically downward direction through the centroid, that is C2. So let us do that. This is C2, and we will be drawing the weight component in vertically downward direction, and we will name it as W2. Then at the contact point E, there should be the reaction force RE normal to the contact point E. So let us do that. This is RE, which is normal to the contact point E. Now for the contact point D, the reaction force RD should act normal to the contact point D again, and that should be towards the sphere Y. So let us do that. This is RD, that is acting normal to the contact point D, and this should be towards the sphere Y. But we can observe that RD on both the sphere at contact point D are equal in magnitude, as both the spheres are in equilibrium, but they are opposite in direction and are collinear, so that they do not appear in the free body diagram. So let us draw the resulting free body diagram for this example. Well, this is all for today, and we will be discussing some more examples relating to the free body diagram in the second part of this series. So if you like this video, please do give it a thumbs up and subscribe to my channel if you haven't already. Thank you.